Every single time a machine moves, you know what happens? We lose energy. Between friction, heat, and vibration is basically this unavoidable tax we constantly pay to the laws of physics. But what if we could actually claw some of that energy back? Well, welcome to this explainer. I am absolutely thrilled you're tuning in today because we are unpacking a conceptual engineering marvel that is practically guaranteed to get your gears turning. We're taking a deep dive into a futuristic experimental platform that explores synchronized electromechanical regeneration.
So let's just start with a massive what-if question. What if machines intelligently recycled their own motion energy? Now, just think about the implications of that for a second. To be clear, we aren't talking about breaking the laws of thermodynamics here. We're talking about working way smarter within them. Just imagine if things like electromagnetic synchronization, gravity-assisted motion, regenerative recovery, and AI-controlled timing could all work seamlessly together inside one advanced mechanical platform. I know, it sounds a bit like science fiction, but today we're going to map out exactly how the architecture of a system like this actually works.
All right, to truly wrap our heads around this, here is our roadmap for the explainer. First, the core mechanical concept, then the anatomy of the machine, third, the regenerative descent system, followed by the AI synchronization brain. Then we'll look at the full machine cycle, and finally, ground it all in engineering reality.
Okay, let's jump right into Section 1, the core mechanical concept.
When you look at the conceptual blueprint for this system, the sheer scale of it is just incredible. What we're dealing with uniquely combines precision electromagnetic actuation with regenerative motion recovery. You see, instead of relying on traditional continuous contact mechanical systems, which, as we know, suffer from massive friction, this system is built entirely around a contact-controlled magnetic architecture. It essentially uses magnetic forces and gravity to do the heavy lifting, and it's designed specifically to maintain really stable mechanical operation while minimizing all that unwanted impact. Moving right along to Section 2, the anatomy of the machine. Let's zoom in and isolate a few specific components, starting from the center of the frame and working our way out.
Right at the very heart of the machine sits the NMP, or neodymium magnet piston. This is your primary moving magnetic assembly. And because it relies on that contact-controlled architecture we just talked about, the NMP drives the machine's synchronized vertical motion with incredibly minimal friction. It is, for all intents and purposes, the central spine of the entire kinetic process.
Now, positioned right above that NMP sits the linear electromagnetic actuator. I want you to contrast this in your mind with a traditional hydraulic piston or a standard impact-based mechanism. Those are all about brute force, right? This actuator, on the other hand, operates using extremely short electromagnetic timing pulses. When an electrical current passes through its internal copper coils, a controlled magnetic field rapidly moves the actuator armature, and it does this with literal millisecond precision. So it's not about raw, continuous power. It's all about perfect, precisely timed bursts.
Which brings us to our next vital component. If we shift our focus over to the right side of the machine's architecture, there's a really distinct section known as the right NMW unit.
NMW simply stands for non-magnetic weight. As that central magnetic piston rises, this solid non-magnetic weight rises right along with it. Why? Well, to basically bank gravitational potential energy inside that elevated mass. And to do this smoothly, the NMW sits on its own independent precision-guided rail. That dedicated guide rail is absolutely crucial because it prevents any unwanted lateral or side-to-side movement. It keeps the vertical alignment perfectly, rock-solid stable as that heavy mass gets elevated.
All right, Section 3, the regenerative descent system. We've lifted the weight, we've stored the energy, so how do we actively capture it on the way back down? The mechanical design here is honestly brilliant. During upward movement, you obviously don't want anything slowing the system down, right? So the generator remains completely mechanically disconnected, zero unnecessary resistance. However, the exact millisecond it begins its downward motion, a one-way overrunning clutch automatically engages. This clutch seamlessly connects the descending weight directly to the flywheel and the generator system, so that gravitational descent physically forces the flywheel to spin. All that stored potential energy from the falling NMW transfers straight into rotational energy inside the flywheel. That flywheel then rotates a low RPM permanent magnet generator. And through the magic of electromagnetic induction, that mechanical rotational motion is instantly converted back into electrical energy. It's wild. We are quite literally harvesting gravity.
But you know, a machine this precise doesn't just run on clockwork alone. Section 4, the AI synchronization brain. We're shifting gears from the mechanical muscles of the platform to its digital nervous system.
This whole setup is absolutely loaded with optical encoders and Hall effect sensors that are continuously monitoring the machine in real time. They are tracking the piston position, the exact motion timing, the incredibly delicate magnetic spacing, which engineers call the magnetic air gap, and the overall synchronization accuracy. And the AI dynamically optimizes all of this on the fly. Say the RPM changes or the load shift suddenly, advanced timing correction kicks in instantly to maintain totally smooth operation.
So, Section 5, the full machine cycle. Now that we've got the pieces, let's put this whole thing in motion. Walk through this continuous loop with me. Step 1, the AI tells the linear electromagnetic actuator to deliver a perfectly synchronized millisecond pulse. Step 2, that exact pulse causes the NMP and the attached NMW to rise vertically, fighting gravity and banking immense potential energy. Step 3, as it reaches top dead center and starts to fall, that one-way clutch automatically engages. And finally, Step 4, the falling weight accelerates the flywheel. The permanent magnet generator kicks in and electricity is produced. Then, the system simply returns to its starting position, resets, and the cycle repeats.
Now, to run a relentless cycle like that, you need some extreme durability. That's why the architecture relies heavily on advanced engineering materials. We're talking carbon fiber composites, ceramic linear bearings, specialized aluminum alloy structures, and reinforced industrial frames. These specific materials are chosen to drastically reduce the reciprocating mass while keeping the structural rigidity sky high. Plus, they help dissipate the intense heat generated by those electromagnetic coils.
And hey, speaking of heat, that brings us perfectly to Section 6, Engineering Reality, Thermodynamics in Action. It is super important that we anchor this explainer firmly in the real world here.
Because we need to dispel some myths. Is this a perpetual motion machine? Actually, let me just stop right there. Absolutely not. It requires external energy to run. Does it violate physics? No way. It completely obeys the laws of thermodynamics. Is it 100% efficient? Never. And most importantly, this is not a free energy device. It is specifically designed as a partially regenerative cycle.
And the reason it's only partially regenerative is due to unbreakable physical realities. The machine will always suffer unavoidable energy losses, friction between moving parts, heat bleeding from the coils, electrical resistance in the wires, magnetic hysteresis inside the materials, and system vibration. All of these things continuously drain energy out of the system. Like I said, you just cannot defeat physics.
But here is the magnificent silver lining in all of this. While the system definitely loses energy, the electricity generated by that falling weight and spinning flywheel is beautifully recycled. That recovered energy is fed directly back into the machine to assist its own internal systems. It helps power the actuator timing pulses, the synchronization electronics, the sensor systems, and the control modules. By powering its own brain and its own spark, the total amount of external energy required to keep the whole machine running drops significantly.
Because at the end of the day, the ultimate goal here is simply to improve efficiency through intelligent kinetic energy recovery. Now, this specific architecture is a conceptual exploration, sure, but future iterations of systems like this could integrate things like superconducting components or ultra-high-efficiency magnets. If we can perfect synchronized electromechanical regeneration, the real-world applications are staggering. We are talking vastly improved industrial machinery, highly efficient robotics, and entirely new kinetic recovery tech for transportation. Which leaves us with this final, provocative thought to chew on today. How will intelligent kinetic recovery change the industrial machines of tomorrow? Look, when machines can actively harvest and recycle their own gravitational and kinetic energy, the efficiency ceiling of human engineering gets pushed infinitely higher. The system we explore today is just one possible direction, but it proves that a future where synchronization, regeneration, and AI operate together as one integrated unit, well, it isn't just a dream, it's a mechanical inevitability. Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.